Right, so yeah, as Penny mentioned, my talk is going to be about how we use geophysics to understand and mitigate risks, mainly on the consulting, engineering, and environmental projects that I deal with. And in this field, we find there's two types of people. There's those that like geophysics, and then there's those that don't. And those that don't, it's usually because they've had a bad experience. They may have been promised a result, and it wasn't what they were expecting. Part of the real challenge in delivering a successful project is communication. Understanding clearly how the geophysics is going to reduce the risk profile on any particular project. And it's about storytelling, and I think that's been clear today that communication and storytelling is a big part of like how you get your message across to reduce risk. So I'm based in Calgary. We do a lot of work in the infrastructure and environment sectors. So typical projects we would work on, things like we do a lot of work in the Alberta oil sands. We do municipal work, for example, this light rail transit line in Calgary that we hope will get built. And we do a lot of work on pipeline projects. Now, all of these projects require an understanding of what's going on in the top few meters beneath the ground. So ideal in that shallow veneer of the earth where you have this complex interaction of rock, soil, water, air, and living organisms. And it's a multidisciplinary study, and geophysics is just one piece of that puzzle. So it's giving you just a part of the picture of what's going on underground. So for those not familiar with the types of methods we might use in near-surface geophysics, basically we're using different techniques to measure a physical property that we can then relate back to the soil or the water conditions, for example. And we may be measuring the way that seismic waves travel through the ground, or measuring how well soil or rock conducts electricity. That can tell us something about the geology underground. So why would you do geophysics? Well, yeah, the big advantages are it's non-invasive. You get spatially continuous data, so you can connect the dots between your point measurements. And some of the positive impacts that it can have on projects are there's minimal environmental disturbance. You're not clearing trees where you don't need to. There's reduced ground disturbance, so there's less of a need to, you can drill fewer boreholes or excavate fewer test pits. You can also, if you get out in front and do your geophysics in advance of these projects, you can optimize your drilling programs. And we can also get data from areas that we might not otherwise be able to get data from. But I need to caution that geophysical models are not a perfect snapshot of what's going underground. But they do provide important data that if you use it effectively, it can really help you out. And just to demonstrate, I'm going to show 3 different case studies here. The first is we had a client who was building a pond embankment in Alberta, and they needed to source 40,000 cubic meters of sand in order to build this embankment. So they had a permit for a borrow source investigation area, and they commissioned a geotechnical investigation. And so this is kind of what the site looks like. This gray scale image here is the topography. The red dashed lines, the permit boundary they had for this investigation. And our geotechnical team went out and they dug a series of test pits. And we've plotted them here in leapfrog view. These colored cylinders here, the yellow colors show where we have dominantly sand, and the blue colors where we have silt, green. The blue color is more clay, green, silt. So we did this first phase of the investigation, and the client said, okay, do I have 40,000 cubes of sand? And our engineers said, we don't know. So they came back to our geophysics group and said, what can you do to improve on this? So We undertook an ERT survey, electrical resistivity tomography, and we're just, again, measuring how well the soil conducts electricity. And sand is quite resistive. Finer grain materials like clay is less resistive. So it's a good tool for differentiating between clay and sand. And we found we had pretty good correlation. You know, the red dots here are where you have that resistive sand material. And it was lining up quite well with where we were seeing sand in the test pits. So we'd been able to use this data to interpolate what's going on in between those test pits. We then took those high resistivity values that we could correlate to the sand and said, let's look at this distribution. Let's put it into Leapfrog Works and let's do just some basic 3D modeling. Someone referred to it as a lava lamp. Oh yeah, Scott referred to it as a lava lamp model. This is a lava lamp model. And there's a bit of subjectivity involved here, but we could come up with a range of how much sand you're going to have here. We've plotted this orange isosurface. This is of what we thought, based on the data we had, is the minimum amount of sand there, and it was 36,000 cubes. On the more optimistic side, if we kind of push the limits a bit more, we said you could have as much as 43,000 cubes there. So they were right on the button of that number. But we said, hey, you know, you look at this, you've got this borosource boundary. Why don't you just change your permit and push it further out this way? And you're likely to get that extra sand that you need to build the embankment. Using Leapfrog Works, we could also come up with this excavation plan. We also knew where the groundwater level was, and we could make assumptions about how much of this material was recoverable based on where that water table was. So we came up with a design plan for them to do the excavation. And in my second example, this is for a limestone mine in northern Alberta. We're doing this project with Hammerstone Corporation. And this is the active mine here, and they wanted to expand their operations further south in this direction here. But they were encountering problems. Well, firstly, they wanted to recover the high-grade limestone unit, and they're coming across lots of, as is common in limestone, karst dissolution features. And these are a problem for two reasons. It lowered the quality of the rock, and they're also a geohazard. When they're mining, these were collapse features that were impacting their mining operations. And just to show you how that looks like on the quarry face, yeah, the clean limestone unit is down here, but you have these deeply incised karst features here, which are a real problem. And they were tough to predict, you know, where they were occurring. This is just a cross-section taken ahead of the quarry face. Well, after they'd mined it out, this is the cross-section they recovered. And they'd mainly been using drilling to try and delineate these features. But this red line just shows that highly irregular top of limestone surface. And based on 23 boreholes, they were able to identify some of these karst features, but they were missing a lot of the details here. In particular, they didn't even know about this one, and this one here as well. So they came to us and said, you know, can you use geophysics to help map out these karst features? And looking at this, we said, you know, we're probably not going to be able to recover exactly the shapes of those karst features, but we can probably tell you where they are in their spatial distribution. So we used a technique called, we used the seismic refraction technique, where we're just essentially measuring the compressional wave or the P-wave velocities of the material. So hard rock is fast, slow, loose soils are slow. And on this figure here, we have the geologic cross-section underneath, and on top, this semi-transparent colored grid here is the refraction data. And we found there's a very good correlation between where you get these lower velocity anomalies and these karst features. So it was quite successful at seeing those features. We also did some electrical resistivity tomography here, and we found that these karst features, they were being infilled by a more resistive sand, so the ERT was also somewhat predictive in where these features were occurring, but we found that the refraction on its own was good enough to use as a predictive tool. And just to put it into context of how we're doing this, let's start this video. So this is the mine. They wanted to advance into this area here. This is the top of limestone elevation surface, and you can see this is an area of irregular topography that they'd mapped out. We got some seismic refraction profiles further ahead. We removed the slow velocities to show the top of the limestone surface, and then we removed the even faster velocities to show where you likely had these karst features as well. So this gave them the information they could take to go on and make decisions about where to expand the mine. So I want to move on to my third example here, and this is moving across the world to Bangladesh. This is a picture of the Kutupalong refugee camp. It's currently the largest refugee camp in the world. And the population of this camp and the other satellite camps around here is almost 1 million people. So to give you some background on this, the Rohingya people have been coming to Bangladesh since the 1970s, but in August 2017, the Myanmar military had a violent crackdown on the Rohingya villages there, forcing them to flee across the border into southeastern Bangladesh, close to the city of Cox's Bazar in Bangladesh. And they were lacking, they had immediate needs for security, for food, but also for water. And UNHCR had asked us if we could help them out with a groundwater exploration program. So we went over there shortly after the crisis began. And we were working in two areas on the Teknaf Peninsula here in Bangladesh. There's generally two areas of the camps. On the northern peninsula, you have the Kutupalong and Balukali camps, which are the really big mega camps. And in the south, there's a couple of camps, the Nyapara and Leda camps. Now, in the north, water wasn't such a problem. Finding water, there was plentiful water that was being supplied from these shallow hand pumps. The problem was that it was severely contaminated because in the rush to build these shelters and install whatever infrastructure they could, latrines, there were contamination issues, and the shallow aquifers were being contaminated. In the south, we had a different problem. They didn't have enough water. During the pronounced dry season in Bangladesh from October to April, these shallow aquifers, they just get completely depleted, and they don't get recharged again until the monsoon season comes around again. So we brought equipment over there. Again, we were doing ERT because it's a very good tool for finding these more granular, more permeable type aquifers that would be suitable drilling targets for water wells. We also brought a UAV with us, which was an invaluable tool for helping plan out our lines. One of the challenges, as you can see here, is there's just so many people and structures and houses. We really had a challenge finding straight lines through these areas, and the UAV helped us plan ahead and locate our survey lines. So we started in the south, near the Nyapara and Leda camps, and we're working on the hypothesis that there were these sandstone ridges that extended along the peninsula here, and we thought that there might be a continuous sandstone unit under there that would be a good unit and a good aquifer to target. So we started surveying in the north where we knew we had sandstone outcrops. This UAV photo here shows the ortho photo, and you can actually see these ridges based on the vegetation here, A and B. We got a line of ERT across here, and we found that, these sandstone units were quite resistive, but unfortunately there was no continuity between them. So just looking at them in cross-section, these aren't very big aquifers that will yield a lot of water. But we thought maybe if these ridges extend further south, they maybe have higher potential. And so we did additional ERT lines further to the south, and we're actually able to map out these ridges quite clearly. And they came very close to the two camps down here. So they were likely very good targets for putting in new wells. But we also wanted to know, we didn't really know anything about the hydrogeology of these aquifers. So what we did was we did a very crude survey. We went out in the villages and we just mapped out where are all these shallow hand pumps that only go down less than 10 meters that run dry. They're obviously not very good well locations. We also found some very good, relatively high-producing wells with good yields that some of them even have motorized pumps on them. And talking to the landowners, we got a sense of how deep these things were. So in our leapfrog model, we just plotted up where we had these good wells as these green cylinders here. And we found this very good correlation between where we had resistive targets here. So this was a good sign for helping plan out the surveys. And then the challenge was we were only there for 2 weeks, and we knew once we'd left that a lot of the information we gathered might be lost. So it was really key for us to get a 3D model together while we were in the field, and we actually went into the camps, we talked to the NGOs who were drilling these wells, the various stakeholders, and we would just bring up our model and say, these are good spots to drill here and here, and we had the topography maps with our recent orthophotos overlaid to help show them where they had good locations to drill. Then we moved north to Kutupalong, and this was a different story. And the Google Earth imagery from earlier that year told the story. This is the background image here that we plotted in Oasis montage, and you can see it's relatively undisturbed terrain. These mosaics here are from our UAV drone surveys, and you can see just how quickly that area was transformed by these hundreds of thousands of people who came here, just found any flat land they could find, usually on the hills and sides of these hills here, and they constructed their quite simple shelters out of bamboo and tarpaulin. These white lines here are where we were able to get ERT profiles. And we wanted to get a rough cross-section through the camp that would show us some information about the shallow geology under the camps. But again, the real challenge was finding straight lines in these areas. And just to exemplify that, here's a zoom in on one of our UAV photos. You can just see it's just this chaotic arrangement of shelters. We actually found the best places to put our profiles where we could get a reasonable straight shot was in the valleys in this area because no one was building shelters but in those locations. But the reasons why they weren't building shelters there was because that's where a lot of the effluent and the sewage was going in there. So it wasn't the nicest conditions to do a geophysics survey, but fortunately none of us got seriously ill doing that. And then we, again, wanted to display the model in 3D that we could communicate with the various NGOs. This time we had some drilling information from a program further to the north. So putting that together in Leapfrog View, we could correlate these sandy gravel units with the more resistive features. And here we wanted to target deeper aquifers with a more impermeable clay cap. The reason why we're targeting those slightly deeper aquifers was because we thought they would be better protected from the contamination that was causing these problems in these shallow aquifers at surface here, where all the thousands of hand pumps were being installed. So I just want to quickly show this last project that we're actively working on. It's in Warsaw, Poland. We are working in an area that was formerly the ghetto during World War II. And it's a site called Mila 18. And this is where the Jewish resistance fighters in 1943, where they had their last stand when the SS troops were coming in to liquidate the ghetto. It's the subject of a good book by Leon Uris called Mila 18. What happened at the site is they retreated to one of their bunkers. They had these underground bunkers all over the ghetto. And unfortunately, the bunker was found. It was gassed. The entrances were blown up. And it's estimated that about 100 people died and still remain in this underground tomb, basically. Now, the site was never developed after the war. Warsaw was completely leveled in 1944, but they rebuilt, but they kept this area relatively free. And so the Warsaw Ghetto Museum invited us to come to the site and see if we could use geophysics to see what remained of the bunker underground. And so we used Leapfrog Works to pull all this information together. We had some historical street maps that helped us see where the footprints of those former buildings were. We had multispectral imagery from a drone that showed the former streets. Some of the most tantalizing data is this resistivity data. We're getting these high resistivity blobs here, which we interpret as air-filled voids or pockets that are still open underground. So we think parts of the bunker are still intact. But yeah, that's my talk. Thank you.